Welcome to the sum and product puzzle, also known as the impossible puzzle. You are free to use any programming language as you will need tables of numbers to solve this. So here is the puzzle. Sam and Prudence are two great mathematicians, and they are trying to find two integers, m and n, which are between 2 and 50, inclusive. Only Sam knows their sum, and only Prudence knows their product. They then have this dialogue. Prudence: I don't know your sum, Sam. Sam: I knew you didn't. Prudence: Now I know your sum. Sam: And now I know your product. What are m and n? I'm going to give the solution now. First, let's look at the possible numbers Sam can have. Since m and n are between 2 and 50, then Sam can have any number between 4 and 100. Suppose Sam has the sum 8. Then the possible pairs are 2 and 6, 3 and 5, and 4 and 4, which means Prudence would have either 12, 15, or 16. If Sam has the sum 9, then the possible pairs are 2 and 7, 3 and 6, and 4 and 5, which means Prudence would have either 14, 18, or 20. If Sam has the sum 10, then Prudence would have 16, 21, 24, or 25. This is a large table of numbers I made using Python. The numbers on the left are the sums, and the numbers on the right are the possible products for that sum. For example, if the sum is 15, then the number Prudence can have is 26, 36, 44, 50, 54, or 56. Notice that products can be repeated. For example, the product 20 with the sum 9 and with the sum 12. I also have another table below which shows how many times each product appears. For example, if the sum is 7, then the first product appears once and the second product appears twice. Let's view these two tables side by side. Notice that there are products which appear once, and since these products are unique, that means if Prudence had one of these products, then he would be able to figure out the associated sum. For example, if Prudence had the product 9, which only appears once, then he would know that the sum Sam has is 6, since no other sum is associated with the product 9. Now let's look at the original dialogue. Prudence said that he didn't know Sam's sum, and Sam said that he knows that Prudence cannot figure it out. But how would Sam know that Prudence cannot figure out the sum? This is only possible if Sam has a sum which has no unique products. For example, if Sam had the sum 23, all the associated products appear multiple times with other sums, so there is no way Prudence would be able to figure out the sum if his product was one of these. So what did we learn so far? We know that Sam has a sum with products that are not unique. It's how he was able to figure out that Prudence can't know the sum. Since there are multiple sums with no unique products, let's group them together in another table. We then end up with a new table with 10 sums. Next, Prudence says, "Now I know your sum." What product could Prudence have had for him to say this? If Prudence had the product 30, he would have said, "The sum is either 11 or 17. If Prudence had the product 132, then he would have said, "The sum is either 23, 37, or 47. The only way Prudence could have said, "Now I know your sum," is if the product is unique in this table. Let's see how many times each product appears in this new table. We see that the products like 18, 24, and so on appear only once, so if Prudence had any of these products, he would have figured out Sam's sum. Now let's look at the original conversation again. Prudence says, "Now I know your sum," and then Sam says, "And now I know your product." But what sum did Sam have that let him figure out the product? Let's look at our tables again. If Prudence had the product 28, he would know that the sum is 11, because 28 is a unique product. But if Sam had the sum 11, then he wouldn't know what the product is, since there are many unique products. So Sam would have then said, "Your product is either 18, 24, or 28. But instead, Sam said, "I know your product." So let's look at our tables again. For Sam to know the product, there should be only one sum that has only one unique product, and that sum is 17, with the product 52. So with the sum 17 and the product 52, this conversation now makes sense, and this leads to our solution. If the sum is 17 and the product is 52, then the original integers were 13 and 4.